Cool. So hello everyone. Welcome to today's early career researcher takeover. That does sound a bit sinister, I think. It sounds like we've hacked our way into the UKCCSRC network. But we haven't. We're just here to present some good research. And last week we had our first early careers presentations, and this is part 2 of that. I think it's come at quite an interesting time with Boris's 10-point plan for a green recovery yesterday. Looking to decarbonise energy in the UK, step towards meeting carbon budgets, and more importantly, funding for CCS. So we've got an hour to go through 3 presentations. First up, we've got Louise Hamdy from Swansea. Then we've got Mikhail from Brunel and Grazia from Imperial. They're going to have roughly 10 minutes each, followed by 10 minutes for questions and answers. So generally, try to give the presenters 10 minutes for their presentation, and then if you want to pop any questions that you have that come up in the chat, and then we'll go through those at the end. So first up, we have Louise Hamdy. She'll be presenting on hydrophobic inclusion-induced void space for enhanced air capture of CO2 by novel polyamine adsorbents. I'll give a quick intro to Louise. Louise is a postdoctoral research officer for Flexis at Swansea. She completed her master's at the University of Glasgow, and she obtained her PhD in supramolecular chemistry from the University of Bath. Her interests lie in the area of functional materials with particular focus on adsorbent properties, and she's currently working on the development of cross-linked polymers for carbon capture. Over to you, Louise.
Thank you. Can you see my screen?
We can.
Okay. Well, thank you, Dermot, for the introduction. So today I'm going to be presenting work carried out by my colleague, Athanasios Katsianos, who is now a researcher at the TU Dortmund University in Germany. And I was also involved in this research, and it was also a collaborative effort with several researchers involved. So our work in the Andreoli research group at ESRI is concerned with amine-based adsorbents, so for CO2 capture. And amine-based adsorbents are widely acknowledged to be ideal for direct air capture of CO2 because of their selective adsorption with CO2 and their ability to adsorb CO2 under low concentrations. However, many polyamine-based adsorbents suffer diffusion limitations. So this is they lack the ability of CO2 to enter the pores of the materials and come into contact with the amines and thus be able to adsorb the CO2. We have found, looking at unsupported cross-linked polyamine adsorbents, that introducing a hydrophobic additive into the material is beneficial for the CO2 uptake. So in this research, we've produced a new adsorbent, and we've determined the actual origin of this higher CO2 uptake capacity at lower temperatures. So the material that we made was a polyallylamine, which only contains primary amines, which are generally the most effective for CO2 adsorption. And this amine is combined with a hydrophobic additive and cross-linked with fullerene C60. So we made the adsorbent with the additive and without the additive, PAA C60 and hydrophobic additive, PAA C60. So we use elemental analysis to determine the percentage weight of each component of the materials. And we see that the hydrophobic additive accounts for about 23% of the weight of the additive material. And importantly, the hydrophobic additive material has a relatively less weight percent of amine. So generally, in CO2 adsorption, because adsorption is an exothermic process, it's better at lower temperatures. However, with many polyamine adsorbents, we see that actually the adsorption is better at higher temperatures. And this is because the increase in temperature affords the better thermal motion of the polyamine chains and opens up diffusion pathways so the CO2 can enter the pores, come into contact with the amines. So let me show you the CO2 adsorption of these adsorbents. We see that the black one here, PAAC60, behaves very typically of many polyamine CO2 adsorbents. Its adsorption is highly temperature dependent. At 90 degrees, we get the highest uptake of about 0.19 grams per gram, but at 30 degrees, which is relevant to our direct air capture conditions, around about ambient temperature, the uptake is far lower at about 0.067 grams per gram. Now, this is due to the diffusion limitation of this material. The hydrophobic additive material behaves very differently. We have a far lesser temperature dependence of the adsorption, and importantly, adsorption is actually highest at the lower temperature of 30 degrees. Now, this we can see is due to the hydrophobic additive, but how does it actually influence the material such that we see the adsorption in this way? We think that the additive, being hydrophobic, repels the amines, the polymer chains, and creates diffusion pathways through repulsion, allowing the CO2 to access the amines. Looking at the amine efficiency over in this graph, we see that the amine efficiency of the hydrophobic additive material is very high at 30 degrees, and it's far more temperature dependent for the non-hydrophobic additive material. And 0.3 amine efficiency means there's 0.3 moles of CO2 adsorbed per mole of amine that we have, and this is high for our polyamine material. We also look at the adsorption under air CO2 concentration, so 400 ppm CO2, and we see that the PAAC60 goes through a kind of temperature, a maximum temperature, and whereby adsorption is highest at 50 degrees. But for the hydrophobic additive material, adsorption, as expected from the pure adsorption, is highest at 30 degrees. And this adsorption of 0.053 grams per gram equals about 1.2 millimoles CO2 per gram. And this is on a par with many supported polyamine-based materials. So here we see the adsorption measured at 30 degrees and at 90 degrees for both materials under different pressures from 0 to about 120 millibar. And as expected, we see higher adsorption at 30 degrees for our polyamine material and lower adsorption at 30 degrees for our PAAC60 material, and the opposite at 90 degrees. Now, we use microcalorimetry to measure the heat of adsorption. This is the heat released on adsorption of CO2 at each of these points. And we plot the heat of adsorption against the quantity of CO2 adsorbed. Now, we see first that the heat of adsorption is highest for all the materials on first contact with CO2. So very high, about 100 to 115 kilojoules per mole on first contact. And this is due to the abundant amines on both materials and the formation of the chemisorption interactions, whereby we form ammonium carbamate and carbamic acid species. So on inclusion of the hydrophobic additive, at 30 degrees, we see that the heat of adsorption is essentially increased. And this is due to the fact that the hydrophobic additive allows access to the amines to form the chemisorbed species, whereby at 30 degrees, the PAC60 material is not always chemisorbing, and a lot of the adsorption is due to physisorption interactions, which have a lower heat of adsorption. At 90 degrees, however, we see that the heat of adsorption is effectively lowered on inclusion of the hydrophobic additive. Now, we know that the hydrophobic additive material has lower amine concentration, and these amines are more likely to be more isolated from one another. So we believe that this material is more likely to form carbamic acid. Now, this only requires one amine per CO2 adsorbed, and this has a lower heat of adsorption, whereas for PAC60, which has more amines, it's more likely to form ammonium carbamate, which involves 2 amines per mole of CO2, and this has a higher heat of adsorption. So we carried out simultaneous CO2 adsorption at 90 degrees and Fourier transfer infrared spectroscopy. And in the spectra, we can see for PAC60 and the hydrophobic additive material, the rate of formation of the formed species. And we see that the adsorbed species are formed faster for the hydrophobic additive material. Now, looking at some of the adsorption bands, we can see that there's a bit of a shoulder in PAC60 and a peak, which are more pronounced in PAC60. These are due to the NH deformation vibrations of ammonium carbamate. Also, there's a peak at 690 and a bit more of a shoulder at 1400 for the hydrophobic additive material, and this is due to the CO and the OH adsorption bands of carbamic acid. So we have established that the hydrophobic additive improves adsorption at lower temperatures, but we want to quantitatively determine the origin of this enhanced uptake. So for this, we use positron annihilation lifetime spectroscopy. Now, this PALS spectroscopy measures the lifetime of the orthopositronium state to calculate the free volume of our material. And this is an ideal technique to measure the nano and mesoscale void volume. So the lifetime here is correlated with the size of the void volume. The longer the lifetime, the bigger the void. For PAC60, we see a lower lifetime of this orthopositronium state, and we have a lower radius of free volume. And the hydrophobic additive material has a radius of about 0.04 nanometers larger than the non-hydrophobic additive material. We had a look at some other research and have found that indeed an increase of just 0.04 nanometers is sufficient to improve gas permeability. And this is the origin of our enhanced CO2 uptake. So to conclude, we have developed a new adsorbent, which has a higher CO2 capture capacity and higher amine efficiency than its analog material, which doesn't have a hydrophobic additive. And it's a better adsorbent at lower temperatures. Under direct air capture conditions of 400 ppm and 30 degrees, it adsorbs 0.035 grams per gram. This is competitive with other polyamine-based adsorbents. The inclusion of the hydrophobic additive alters the heat of adsorption, as we've seen, and also the rate of formation of the adsorbed species. So the hydrophobic additive increases the void volume. It gives us larger void spaces, and this opens up better diffusion pathways for the CO2. So finally, I'd just like to thank Athanasios Katsianos for this work and all of the collaborators on this project. And thank you for listening, and I'd like to answer some questions if you have any.
Thanks very much, Louise. That was really interesting. We haven't got any questions in the chat yet, but I'll kick things off. But if anyone wants to add anything into the chat, then please feel free. So my first question, I guess, is around the use of the additive and whether there's any downsides that you're aware of to that. I guess the first thing that springs to my mind is, is it costly? How much price is it going to add on to the generation of your absorbent? Don't know if you know.
Well, it very much depends on the type of additive. So we used one particular additive in this case, but we could carry out the same work using a different additive. And of course, they'll have different degrees of effectiveness. Including the additive reduces the relative quantity of amine that you have per gram, which ideally isn't good. However, these materials that we've produced are not supported. We've not used a silica or alumina support for these materials, so they carry less unproductive waste, you could say, already.
Cool, that sounds good. I guess it's it's early days probably for you guys. Straight away, you can't solve everything. Yeah, we've had a few questions in. Firstly, from David. If the porosity is, or if David's online, then he might want to ask that to you himself.
I am online. Thanks, Louise. My question was if porosity is important for the, I guess, gas diffusion. Have you compared it to things like amine functionalized mesoporous silica, which will have plenty of space for gas diffusion?
Yeah, so much so that you can get a surface area on them, whereas BET analysis, for example, doesn't work on.
Would be pretty bad.
Yeah, the voids are not necessarily permanent, and they are too small to probe effectively. It's a case that they're not it's not a permanent thing. It's a kind of fleeting porosity. The polyamine chains are always in motion, and that's why we need to try and increase the spaces between them, albeit not on a permanent scale.
Great. Does that answer your question, David?
Yeah, mostly. I mean, I was just thinking more from an adsorption perspective in terms of amount adsorbed, heat of adsorption. But yeah, it might be something worth looking at potentially, because I think most of the other amine functionized silicas are not mesoporous or not very mesoporous. But yeah, no, I don't have.
They might not benefit from this because they just suffer from these diffusion limitations due to kind of agglomerations of the polymer in the pores, blocking pores and so on. And there's no reason why they might too not benefit from the hydrophobicity of the amine.
Cool. Thank you.
We might move on to another question that we've had from William Joyce from UKRI. His question is, unless he's there and wants to ask it to you himself, I'll give him a chance.
Yeah, okay. Thank you. I thought it was a really nice presentation, actually, and some really sort of tidy results there. I just wondered, why is DAX used as the model for this? I mean, could this be extrapolated into different CCS systems? And I might have missed it, but why do you add the fullerene to the amine system?
The fullerene is the cross-linker.
Okay.
Because so that we form a porous so that we form a solid adsorbent. So we cross-link we like effectively kind of tether the polyamine chains together into a solid network.
Yeah.
Did
that answer the question on
yeah, I just wondered why DAX though? Why is that the model?
It was what we're most interested in, with the feeling that post-combustion CO2 capture, for example, and relying on more concentrated sources of CO2 isn't necessarily always going to be an option for large-scale CO2 removal, and that we're really interested in developing adsorbents that could be used in direct air capture systems.
Okay, thank you.
Great, thank you for that, and thank you for answering those questions, Louise. With that, I think we'll move on to our next presenter, which we have Mikhail Gorbounov from Brunel University, London, and he'll be presenting on biomass combustion ash in carbon capture. Mikhail is a PhD student at Brunel and works on the biomass combustion ash in carbon capture project, which is supported by the UKCCSRC flexible funding. So over to you, Mike.
Yes, hello, thank you for the introduction. Can you see my screen?
We can, please go ahead.
Oh, well, great. Hello, everybody. As has been said, my name is Mikhail Gorbounov. You can just call me Mike. And today I would like to speak to you about BCA and CC, or biomass combustion ash and carbon capture. It will be of no surprise to you that global warming is kind of a problem, and people worldwide are searching for ways to mitigate climate change. And an integral part of this battle would be implementing the concept of bioenergy, carbon capture and storage, BECCS. This is regarded as one of the most promising ideas for combating global warming. And in fact, 101 scenarios out of the 116 published in the IPC 2014 report, leading to a likely chance of keeping the temperature rise at or below 2 degrees Celsius from the pre-industrial levels, heavily rely on deploying BECCS. This mitigation technique is grounded on two separate concepts, the bioenergy and the carbon capture and storage combined. Bioenergy is the power generated from carbon neutral sources of energy, such as sustainable biomass, i.e. trees, rice cloth, sugarcane, bagasse, energy crops, and so on, and is represented by the letter B on the figure. When being used as the primary fuel for a power plant, the letter E, during combustion, the material releases CO2 that has been absorbed from the surrounding air by the feedstock during its lifetime. And however, this matter does not add new carbon dioxide, and therefore such technologies are considered to be net zero. But by adding CCS to the power plant, we're creating a carbon negative technology, as it does not allow the carbon dioxide in the flue gas, the letter C in the middle of the slide there, to be re-emitted into the atmosphere following combustion. Instead, it's being safely stored underground, which is represented by the letter S. Now, biomass combustion ash, or BCA, can be employed as the capturing media for CO2. And one of the biggest benefits of this material is that it is readily available on site of biomass powered plants. Therefore, the lack of logistic costs make this such an attractive proposal. However, in order to be viable, the ash has to mobilize carbon dioxide. Therefore, biomass combustion fly ash has been extensively characterized and its properties assessed in the context of carbon capture. The surface morphology of the raw fly ash has been evaluated using scanning electron microscopy, SEM. Given the nature of biomass, i.e. non-conductive, the samples were modified prior to analysis, which involved putting the sample on a conductive silver paste to the sample stub, followed by a deposition of a thin layer of gold coating via the gold sputtering technique. The silver paste, though, can be substituted with carbon tape, but as the investigated material might have carbon in it, we decided to abstain from employing it. In any case, as can be inferred from the slide, the fly ash consists of a mixture of spherical particulates with a widely varying size, agglomerations of these particulates, and some porous particles as well. The spherical particles are typical for fly ashes and can be attributed to their amorphous coating formed as a result of relatively abrupt cooling post-combustion. And as clearly demonstrated on the image on the right, the various particles present in the fly ash are not uniform, and there are stark differences in them. But still, you can see a bit of porosity there. Apart from that, the morphology was also studied using the EDS technique. This method of analysis facilitates an understanding of the elements present in the material. And on the slide, you can see the spectrum that we have got. As can be inferred from it, the main constituents of our fly ash is aluminium, oxygen, and silica. These are the prevailing elements, and well, that was expected. Apart from that, we can also find potentially interesting compounds of elements as alkali and alkali earth metals, such as potassium, sodium, magnesium, and calcium, with potassium and calcium being the most prevalent across all the conducted tests. As well, we have some iron and carbon. Also, trace amounts of phosphorus and sulfur have been identified on some of the scans, but the most perhaps confusing thing on the slide here is that we can see gold here, but the SEM and the EDS are done within the same apparatus, and therefore that is the gold sputtering that I have just talked about. Apart from this, we have also conducted an X-ray diffraction analysis, and the results are presented here. The investigated material is, as expected, a mixture of silicates and aluminosilicates with an abundance of inorganic mineral phases such as metal oxides and carbonates. Of particular interest is the potassium carbonate, K2CO3. It is believed to be a substantial contributor to chemisorption of CO2, as in the presence of moisture, the potassium carbonate, the same though could be said about lithium carbonate and sodium carbonate, would transform into potassium bicarbonate, also known as potassium percarbonate, and shown there in the blue hexagon on the slide. And the key thing is that it has only one potassium atom, and this allows for an additional carbon dioxide molecule to be fixed on the other K atom from the original molecule. Similarly, K2O is also a noteworthy compound. Again, in the presence of moisture, the reaction with CO2 will lead to bicarbonate formation, and therefore one molecule of the original substrate would allow to capture 2 molecules of CO2. And that can be said about all of the alkali metals and their hydroxides and oxides, but not about all of the divalent metals. But nevertheless, magnesium oxide has also been found, and it cannot go unmentioned because in the conventional calcium looping process, for example, this chemical compound is used as an additive to the capture media to improve cyclic stability. And apart from that, the carbonation temperature for magnesium oxide is twice as low as for the calcium carbonate, calcium oxide, sorry. Despite that, we have still found also some calcium-containing species, such as calcium oxide and calcium hydroxide, and also limestone, calcium CO3. And despite the calcium carbonate not contributing to the post-combustion carbon capture context, it has probably already captured the CO2 during combustion within the combustion unit as it was formed there. So it has already bound the CO2 emitted during the combustion. It should also be noted that we can see ferric oxide 3, but it is perhaps more suited for carbon monoxide chemisorption rather than carbon dioxide, because upon contact with CO, the reduction process starts to occur. So it goes from ferrum 203 to ferrum 304 to ferrum O, and then finally to pure iron. And during this reaction, CO2 is actually emitted as a byproduct. But this compound can be very helpful for decarbonizing the steel industry, but that's a different topic. Apart from that, we have also done the Fourier transform infrared spectroscopy and the Raman spectroscopy. But the key thing to bear in mind about these techniques is that they are perhaps better suited for identifying organic matter rather than inorganic material and mineral phases. And the reason being that covalent bonds are more prominently displayed on the spectra than ionic bonds. The reason for this phenomenon is the fact that strong ionic bonds do not vibrate strongly after infrared absorbance, i.e. do not change the dipole moment during internal vibrations, and therefore they're less detectable. So the two outermost left peaks on the FTIR, on the left there, have been attributed to the stretching and the bending vibrations of the OH bond respectively. And this functional loop is visible on the spectrum due to one of two reasons. The first one being that it occurs naturally there and is present there within the hydroxides, or it could be there due to the physisorption of water by the surface. Apart from that, both symmetric and asymmetric tensile stretching, as well as bending vibrations for the carbonyl group COO have been identified. The same with OH, they could be attributed to the carbonates present or to the CO2 physically absorbed, but we prefer to stick with the first option for both of them. What is interesting is the silica compounds that we have found. The silica O bonds that were identified by us are probably in the form of aluminosilicates, as their wave numbers of 1,700 approximately suggest the silica O bond with an aluminum inclusion. This redshift phenomena occurs because of the substitution of the aluminum in the tetrahedral position of the silica oxide, which leads to a lower binder energy between the oxygen and the silica, thereby decreasing the stretching vibration from around 1,000 to 1,000, sorry. And a similar thing can be said about the 700 reciprocal centimeters. This bond is typical of kaolinite, a mineral where one tetrahedral sheet of silica is linked with an octahedral sheet of aluminum via an oxygen atom. Moving on to the Raman spectrum, the same limitations are evident. The covalent bonds are more prominently displayed than ionic bonds. However, there's still a myriad of information to be picked up from that. As can be inferred from the slide, the FA is mostly, once again, silicates, aluminosilicates, and carbonates. And the first two phases are confirmed by the peaks closer to the left part of the lower wave numbers. And the D and the G bands carbon there indicate the sp2 carbon hybridization state present in the carbonates in the COO bond. However, previously unconfirmed bonds were also detected. Some bends around the smaller wave numbers are believed to be representative of iron oxides, and these chemical compounds have been identified via XRD analysis, and nevertheless, the Raman has confirmed that assumptions. Another point to mention is that the Raman spectroscopy was conducted at different points in order to cover a wider scope of the material, but the results from them are largely the same. Moving on to nitrogen adsorption and desorption and particle size analysis. So the typical surface areas of ashes is believed to be in the region of 2 to 6 square meters per gram, with coal ashes being on the lower limit and biomass ashes being a little higher. However, our investigated fly ash appears to be much more porous than the others reported in the literature. The specific surface area of the fly ash is approximately 9.4 square meters per gram. In contrast, the BGH pore volume is calculated to be 0.01 centimeters cubed per gram, which is well within the reported range of ashes for both biomass and coal. The average pore diameter is estimated at 7.4 nanometers, which is consistent with the EU PAC technical report that specifies that for type 4 isotherms, the hysteresis occurs if the pores are wider than 4 nanometers, if the tests are conducted under nitrogen and 77 Kelvin, which they were. And the difference between the adsorption and the desorption pattern is clearly visible on the left part of the slide. If we talk about the particle size distribution of the adsorbent, we will see that the most prominent peaks identified were at 12 micrometers, 30 micrometers, 70, and 161. The presence of 4 peaks suggests 2 different theories. The first approach is based on the presence of the spherical particles, as seen in the SEM imaging. Following this logic, we can assume that the identified peaks correlate with the diameters of the round particles found within the fly ash. So this assumption is confirmed by a visual examination of the SEM. On the other hand, the same SEM photos depict that not all of the phases present are spherical. And for situations where one dimension of an object is significantly larger than the other one, with a minimal aspect ratio of 1.5, so 1.5 to 1. That would lead to a bimodal particle size distribution. As the rays shine onto the particle, it will travel along a longer distance on, for example, the x-axis compared to the y-plane, thus leading to formation of 2 different peaks, additional peaks on the spectrum, one for the length and one for the width. Following this theory, we can infer that the particles are of 2 different sizes, with the aspect ratio of both of those being approximately 2.5 to 1. Considering these suggestions from both of these pathways, as well as the manual measurements of the SEM images, our conclusion is that a phase, well, not homogeneous, though the bulk of the material is present in the form of glassy spheres of various sizes, the mineral phases possess a non-spherical geometry, though their particle sizes generally fall within the range of the main peaks described on the slide. Having conducted extensive characterization, we have concluded that the investigated biomass fly ash is a promising material for post-combustion carbon capture. A higher uptake should occur if implementing direct mineralization techniques. And the reason being for that is the high amount of functionalities most suitable for chemisorption of CO2. Therefore, our future work will be focused on the equilibrium and kinetic studies, as well as mass transfer studies. We would like to thank UKCCSRC and EPSRC for supporting our research, as well as the Brunel Research Initiative and Enterprise Fund. And we would also like to thank Dr. Basil Wadi, Peter Clow, and Dr. Ali Nabavi from University of Cranfield for giving us access to the BET equipment. To quickly come back to the functionalities and brag a little bit, our research group has just written an extensive technical review on the surface functional groups, their benefits and drawbacks, the mechanisms of CO2 adsorption, as well as the methods of introducing these functionalities. And this paper is currently available online with the DOE seen there on the screen. On that note, I would like to thank you for your time and attention. Hereby proclaim the Q&A to be open.
Thanks very much, Mike. That was a very good presentation. So thank you for that. We've had a question from David again. Does David want to ask that to Mike himself?
Sure. Hi, Mike. Thanks for your presentation. I guess I just kind of had more of a mass balance style question. So what do you expect the CO2 capacity of your fly ash to be approximately? And per ton of biomass that you combust and the fly ash that you get from that, what proportion of the emitted CO2 can you actually capture?
Okay, so if you don't mind, I will split your questions into 2 halves. So the uptake we're expecting to be about 0.123 millimoles per gram. That is the ones that are relatively commonly found for fly ashes. On On the topic of amount of ash produced per biomass, I'd say that around 4 to 6% is somewhere around the correct mark to estimate how much ash will be produced. I think there is a Scottish power plant, I recently read about it, who burn around 80, no. Well, in any case, that power plant produces around 16 million tons of biomass of ashes per year. And so if they were all to capture carbon, we would get around, I'd say around maybe 20% of the whole emissions, perhaps, from that particular power plant. But to be fully honest, I'm a little hazy on the latter portion.
So in that case, what is your proposed strategy to capture the rest?
Well, of course, adsorption. We're here all about adsorption at Salmon's research group.
Right, but then you have to regenerate your fly ash, right?
Not necessarily. So my preferred logic would be to sequestrate it at the same time. So I don't think there is a need to regenerate the ash. So that whole statement is just, in my opinion, illogical. It's a waste material which we have stabilized, therefore less leaching will occur even if you landfill it. Plus,
right, so for the remaining CO2, you want to do traditional adsorption?
Yes, or perhaps calcium looping. Well,
right, so why not just do that single one for the whole lot?
Oh,
because then you don't need two separate technologies.
Ahead of us, because we are planning to also look into our fly ash as being a proposed additive to other adsorbents to lower the cost, because the key feature of this material is that it is readily available on site, and the logistic costs avoided are obscene. They're going to be very high, and well, let's be honest, the lower the cost, the better the material for implementation at the beginning of the whole process. So right now we need to open the door for adsorption, and lowering costs is one of the options that we can implement.
Thank you both very much. We might just have to follow that up on the side, just in interest of getting through it. Louise has asked a quick question. We'll try and be quick with this one to make sure that Grazia gets her time. How is the fly ash formulated for the absorption? Can it be pelletized?
So yes, it can be pelletized, but I'm not sure what you mean by the word formulated for adsorption.
Just how can it be made into some sort of adsorption? How do you use it in its form, or do you have to formulate it into the pellets or so on? I was just wondering how you make it into.
It would depend on what you want to do. Let's call it that way. Pelletizing is an option, but you can chuck it in as is, essentially. But preferably, of course, we would have to modify it a little bit. But the key point that I'm going to stress once again, that the cost avoidant here, even with pelletizing, if it could be implemented without pelletizing, that would still be better. Unfortunately, it's just too early at this stage for me to talk to you about our particular adsorbent. We have just finished the characterization, and we're just starting our experimental campaign. And as you imagine, the limitations due to COVID-19 are not helpful.
Of course. No, it was really interesting. Thank you, Mikhail.
Oh, thank you.
Yes, thank you very much. So we'll move things on. Thank you very much, Mike. So our next presenter is Grazia Leonzio. She's from Imperial. She's a postdoctoral researcher there, and she's working on the role of power to X in the energy transition project. And today she's going to be presenting on the analysis and modeling of CO2 adsorption from air. Over to you, Grazia.
Okay, do you see my screen?
Yeah, we can see your screen.
Okay. Good afternoon to everyone. The title of this presentation is Analysis and Modeling of CO2 Absorption from Air. The problems treated in this presentation are related to the increase of CO2 emissions to the fact that about 50% of total CO2 emissions are coming from transport sector and small other sources, then there is a problem to capture CO2 from air with direct air capture technologies. Regarding to this, many people look at the process, but many are connected with the companies selling their process. And we want to conduct our independent analysis. What we did find in our research work, we found the values of some key performance indicators of adsorption technology for CO2 capture from air with using different sorbents, such as metal organic frameworks and amine functionalized sorbents. Then we found some critical process parameters for energetic and economic analysis. In this presentation, I'm going to show you a short background regarding CO2 emissions and DAC technologies and companies. Then I'm going to show you our research work, starting from the definition of sorbents and adsorber geometry to show that the Isotherm models, the models for adsorption, desorption cycles, and the validation of this model. Then I'm going to show you results and conclusions. CO2 emissions in the world are increasing in the last years, as you can see in this picture. In particular, in 2018, CO2 emissions were about 37 million ton, and transport sectors and electricity and heat production have the highest influence on CO2 emission. And for this, the temperature increase is increased, and several international agreements were signed to solve this problem. Greenhouse gases removal can have an important role to limit the increase of temperature, and direct air capture is one of these technology, and it can supply CO2 for synthesis processes in the short term, but in the long term is a really negative emission technology with the CO2 storage. And the capacity of DAC technology needed for the future is estimated in order to meet the environmental agreements. For example, in 2030, it is estimated that this technology should capture about 470 million ton of CO2 per year. And we have several companies for direct air capture, and that are divided according to the used technology. That can be an absorption or adsorption that can use variation temperature or variation of humidity for the regeneration. We put attention on Climaworks, that is a company using the adsorption process, and that use a variation of temperature mainly for the regeneration of sorbent. Here, the sorbents that we used in our research work, we used two amine functionalized sorbents, in particular one silica gel-based sorbent and another one cellulose-based sorbent. And we considered three different metal organic frameworks that are MIL 101, MOF 177, and MOF 5, which data are reported in these tables. And also we can see the specification for the adsorber that are provided by Climaworks company. For each sorbent, we defined the Isotherm model that we considered according to the literature works. In particular, for the silica gel-based sorbent, we considered a French model for adsorption and a Langmuir model for the desorption, while for the cellulose-based sorbent, we consider a TOF model for adsorption and desorption. For metal organic frameworks, we considered for adsorption and desorption Langmuir model. Here are the model equations to describe the adsorption and desorption stages. We consider essentially a gas phase material balance for CO2. Then we consider the adsorbed phase material balance and the equation for mass transfer rate. Then we considered also the initial and boundary conditions for the adsorption and desorption that you can see in this slide. The model was validated by laboratory data using a silica gel-based sorbent. In the experimental work, others found that the complete breakthrough can be obtained in about 24 hours, the same time that we found in the model, as you can see in this breakthrough curve. Okay. Then here are the results. We can see the CO2 concentration, the loading, and the breakthrough curve for the silica gel-based sorbent for the adsorption stage, and here for the desorption stage. Also, we have the results for the cellulose-based sorbent, in particular CO2 concentration, loading, and breakthrough curve for the adsorption stage, and here for the desorption stage. And here we have the results for MIL-101 sorbent, in particular the results for adsorption in terms of CO2 concentration, loading, and breakthrough curve, and here for the desorption that is carried out with the temperature swing adsorption. Here the results for MOF-177 sorbent. We have the results for CO2 concentration, loading, and breakthrough curve for adsorption and for desorption. And here for MOF-5, the results for absorption in terms of CO2 concentration, loading, and breakthrough curve, as well as for the desorption stage. Here we can see the general results, and we have two main important results that are the fan power and energy for regeneration. We can see that for amine functionalized sorbent, the fan power has an order of magnitude of about 300, while for metal organic frameworks, this parameter has an order of magnitude of about 1000. Also, we can see the great value of energy of regeneration for metal organic frameworks, and this is due to the low working capacity, then due to the lower equilibrium loading that is a critical parameter for adsorption, influencing the energy of regeneration and then the operative cost. Overall, we can see the higher values for energy consumption for metal organic frameworks compared to the amine functionalized sorbent. Here, a short economic analysis and a comparison with the Climeworks company that use the cellulose-based sorbent. And that is the same used by us in the absorption process. We can see a good agreement in terms of operating conditions and energy consumption. And but we have higher values for cost, and this can explain it by the fact that we consider only one adsorber, but while Climeworks company uses 18 adsorber. Also, we can see the higher values of operating cost for metal organic frameworks due to the higher values for energy of regeneration. In conclusion, we developed a model for adsorption and desorption for amine functionalized sorbent and metal organic frameworks, and we found that the cellulose-based sorbent has lower energy requirements in terms of fan power and energy for regeneration, and there is a good agreement with the Climeworks company. We found that MOF have higher values for energy regeneration due to a lower value of equilibrium loading that can be considered a critical parameter for the absorption. Also, this sorbent have an electricity consumption higher than amine functionalized sorbent, but similar to those reported in the literature. And we have costs that are higher than Climeworks due to the different economy of scale. Here are the reference, and thanks for your attention.
Thank you very much, Grazia, and sorry for introducing the project that you were on earlier wrongly. Quite hard to find information about online, so my mistake for getting it wrong. So we've had some questions on the chat from David. If anyone else wants to chip into that, feel free. So I'll read them out for David, seeing as he had to leave. So the first question was, how do you decide the cycle time for each adsorbent? And secondly, what proportion of the regeneration energy is due to water desorption?
Okay, we decided the cycle time for each adsorbent according to the breakthrough curve. We decided to achieve the 90% of the equilibrium value. This is for absorption and desorption cycle stage.
Great, thank you. We've had one more question from Phoebe. Phoebe, are you there? Do you want to ask that yourself?
And we consider only CO2 and not water. So,
hi, so my question was about the adsorption cycle. So in the final table, you have the comparison between all of them, and one has like a cycle of 89 hours or so. So I was just wondering how practical it is to implement that kind of adsorbent in large scale, given that it had a very high adsorption capacity in comparison with the others. So I was wondering about the balance of if it's usable or not.
Yeah, because do you mean the
I think was the fourth column, something like that, in the table.
Fourth column, the cycle per day.
So I wasn't able to memorize the names, but in one of them, most of the cycles of the first two were kind of 0.1 or 0.2 hours, and then the other one was 89.
Yes, because if I remember well, we considered the full cycle, how many hours are how many hours is one full cycle in considering adsorption and desorption. One day is 24 hours, and then we did the ratio between these to find how many cycles per day.
Yeah, I was just wondering about practicity of having such a long cycle. Like if you wanted to do a large scale facility, is it practical to have such a long run with each regeneration?
I think that for an industrial absorption process with moth is not patent, so it is only in laboratory experience. So this can suggest you that moth is not suitable for an industrial process, and also because it is only a physical absorption and not a chemical absorption. Okay.
Thank you.
Thanks very much, Grazia. So I think that's it on the questions, unless anyone else wants to come in with something.
I actually had something, if I may. What were the regeneration conditions? Was there a pressure swing?
Temperature.
It was just temperature.
Yes.
Okay. Okay.
Is that okay, Louise?
Yeah. Thank you. No, it was just really interesting that the amine-based adsorbent they showed a lower overall regeneration energies, and we normally think of them as being higher, but as you said, it was the different loadings. Thank you.
Yes, the adsorption is a 25 Celsius degree, while the desorption is a 100 Celsius degree.
Okay. Thank you.
You're welcome.
Great, thank you very much. Is there any more questions? No, if not, thank you very much to our three speakers today. Very well done, Louise, Mike and Grazia. They were really good presentations, enjoyed them a lot. Thank you very much. So I'll hand back to Rachel. I think she's going to give a bit of an intro of what we're doing next week, which I think includes some of my work, so it should be good.
Okay, so yeah, thank you everyone. Thank you so much for fantastic presentations, and thank you so much for chairing as well. Our ECR takeover number 2 has been fantastic. So I think on the back of this success, we'll probably be looking to do something again like this, as it's been really interesting to hear from you all and to have some good questions and discussion. So yeah, just to let you know about next week, Thursday 26th of November, 3 till 4, we've got the topic is meeting net zero and the role of CCS, and that's with Claire Goff from the University of Manchester. So that's our last session of this current series. We'll let you know what's going on next after Christmas. Hope to see some of you there. Okay, so bye for now.
Thanks very much, Rachel. Bye, everyone.
Thank you, everyone.